All right, today we're diving into something pretty wild, the invisible architecture behind some of the biggest machines humans have ever built. We're talking about particle accelerators, and more importantly, we're going to look at the amazing software that lets us design them in the first place.
I mean, just think about that for a second. How on earth do you design a machine that's miles long to study particles you can't even see? These things are moving at basically the speed of light. You can't just, sketch something on a napkin and hope it works. Nope. You have to simulate everything, down to the tiniest detail before you even think about laying the first piece of concrete.
And that's where our story starts. The solution we're talking about today is a powerful tool called BMAD, and its story begins right here at Cornell University. This is where a group of physicists realized there had to be a better way to design these incredibly complex machines.
Okay, so let's get into it. Section 1, Simulating the Invisible. What's the actual problem that physicists are up against here?
Well, what they really need to do is build a perfect digital twin of the accelerator, a complete simulation. They have to predict the exact path of every single particle, which means accounting for these unbelievably powerful magnetic fields, and even the tiny, subtle ways the particles themselves interact with each other. I mean, the level of complexity is just staggering.
So, faced with this massive challenge, how did the team at Cornell tackle it? Well, that brings us to our next section, a toolkit of bricks. See, instead of trying to write one single monolithic giant program to do everything, they did something a lot smarter. They chose a much more flexible path. What they created is called a software toolkit. And honestly, the best way to think about it is like a toolbox. It's just filled with all these pre-made, pre-tested little pieces of code, they're called routines, that handle very specific physics calculations. So if you're a developer, you don't have to build a new wrench every time you see a new bolt. You just grab the tool you need from the box. It saves so much time.
And this really gets to the heart of the idea. On the left, you've got the end goal, right? This super complex, precise simulation. And on the right, that's how you get there. A collection of simple, reusable building blocks. BMAD is the glue. It's the system that lets you connect all those simple pieces to build something incredibly complex. You know, the source material puts it perfectly. It says, a toolkit is like a bunch of Lego blocks. And that's exactly it. Each block is a little piece of code that does one thing, and does it really, really well. And just like with Legos, you can combine them in basically infinite ways to build whatever you can possibly imagine.
So why does this matter? Well, this whole Lego approach has some huge advantages. For one, it slashes development time. It also cuts down on bugs and errors because you're using pieces that have already been tried and tested. Plus, it creates a kind of common language, so scientists can share information and designs much more easily. And maybe most importantly, it's safer. If one little brick has a bug, it doesn't bring your entire creation crashing down. All right, so let's track how this whole idea evolved into the powerhouse it is today. That takes us to Section 3, From Baby to Behemoth. Believe it or not, BMAD had pretty humble beginnings. Back in the mid-90s, it started as what they called a modest project with a really cute name, BMAD. And all it did was a few simple calculations for Cornell's own particle storage ring. But then, something amazing happened. More and more scientists started adding their own bricks to the toolkit. It just grew organically and eventually turned into the massive, open-source, collaborative project we see today. And when I say massive, I mean it. Today, the BMAD toolkit has over 100,000 lines of code. That's just incredible. It's a real testament to decades of work from physicists and programmers all over the world. It really did go from a baby to a true behemoth.
Okay, so that brings us to Section 4, Building with BMAD. We've got this giant, amazing box of Legos. The big question is, what can you actually build with it?
Well, the answer is a whole ecosystem of specialized programs. If BMAD is the box of bricks, think of these as different instruction manuals for building very specific things. So you've got TA, which is for general-purpose design. You've got one just for the muon G2 experiment. Another one, called LUX, is all about tracking X-rays. The list just keeps going, and each program is built from the same BMAD bricks, but tailored for a totally different mission.
Now, out of all of these, the one you really need to know about is tau. This is the starting point for pretty much everyone. Sticking with our analogy, if BMAD is the box of Legos, tau is that big main instruction booklet that comes in the box. It lets you quickly put the bricks together, check your design, see how it's all working. So yeah, if you're new to this world, tau is step one. Okay, this is all cool in theory, but let's look at a real-world example. In our final section, the Master Builder's Creations, we're going to see what happens when you use these tools to tackle one of the absolute biggest questions in all of physics.
And that brings us to the Fermilab Muon G2 experiment. Look, this is not just some random project. Its goal is to test the standard model of particle physics. I mean, that's literally our best explanation for how the entire universe works at a fundamental level. If the results from this experiment don't match what the theory predicts, it could change everything we know about physics. The stakes are about as high as they get.
And you can bet the simulation challenges were just immense. They had to figure out exactly how these particles called muons, think of them as a heavy cousin of the electron, how they get into the machine, how they scatter off the walls, how they're steered by these crazy complex electric fields. And they had to do all of that before the muons decay, which they do very, very quickly. I mean, every single one of those steps is a massive physics problem on its own.
So how did it go? Well, one of the developers on the project said it perfectly. Because they could use the BMAD bricks, they weren't starting from scratch. He said the toolkit reduced the development time and provides a flexible framework for future program modifications. In other words, it made the impossible possible. And it made it adaptable for the future.
And that, right there, is the real magic of this toolkit idea. It's not about building just one program for one experiment. It's about empowering a whole community of scientists with the ability to create their own tools for discovery. It kind of proves that sometimes the most important thing you can build isn't the final, flashy machine, but the simple blocks that let everyone else build the future. Which leaves us with a pretty exciting question, right? If these are today's building blocks, what are tomorrow's physicists going to create?